This is the video lecture over section 3.1, which the authors have vaguely entitled Terminology. Terminology of what? What are we even talking about? Well, this unit is about probability, and in this section the authors are going to lay out some of the basic terms related to probability. And the most obvious thing to do is to start with the definition of probability. The probability of an event is a number between 0 and 1 inclusive, which quantifies the likelihood that the event will occur. So a probability is basically a numerical value that tells you how sure you can be that something will happen in a given scenario. Let me point out a couple of things about my definition here. First, I cheated and used the word event without describing exactly what it means. Now, informally, an event is exactly what you'd expect it to be. It's something that happens. We use the word event in everyday conversations, and it's pretty much the same thing here. A little more formally, an event is an outcome or a collection of outcomes in a probability experiment. So it's a potential observation that you're wondering about in an experiment, in a scenario. Will this thing happen or not? That's an event. Secondly, I used this word inclusive. I said that the probability of an event is a number between 0 and 1 inclusive. What does that mean? Well, that means we're not literally going between 0 and 1, but we're also including the bounds. When a math person says between, they usually mean strictly between. They're not including the bounds. So nerds like me have to write the word inclusive when I want to make sure it's clear that you can pick the boundaries, the endpoints. So a probability can be 0. And when the probability of an event is 0, that has a certain implication that we'll talk about later. And the probability of an event can be 1. And it turns out that when the probability is 1, that means something special as well. And the probability could be between 0 and 1. So when we say inclusive, it means we're including the bounds as potential values of a probability. Probabilities can be 0, probabilities can be 1, probabilities can be between 0 and 1. The last thing I'd like to point out about my definition is that I opted for 0 and 1. Rather than saying that probabilities are between 0 and 1 inclusive, I could have just as easily said that they're between 0% and 100% inclusive. It's very common to describe probabilities in terms of percents, but it's not necessary. We could just as easily use fractions or decimals, as long as those numbers are between 0 and 1 inclusive. Now what we want to do from here is come up with some additional terms that will make the definition of probability solid. We want a solid foundation for describing how one would calculate probabilities. So we need a couple more definitions, and then we'll come up with a method for finding probability. A special kind of event is what we call a simple event. A simple event is an event which cannot be broken down into more basic outcomes. Now that definition is going to seem a little bit vague right now, but basically going back to our definition of an event where we described it as an outcome or a collection of outcomes, a simple event would be a single outcome rather than a collection of outcomes of all of the possible things that could happen in the probability experiment. I'll try to make that a little more clear when we get to an example. But let me knock one more definition out of the way. A sample space is a collection of all simple events for a given probability experiment. So if you make a list of everything that can happen, and all the things that you have listed are simple events, we call that a sample space. Quick bit of notation here. We use a capital S to denote a sample space, and you'll notice that when I wrote my capital S on the screen here, I put these little hooks on it. That's just so you know that it's supposed to be a capital S and not a lowercase s. Remember, we've reserved lowercase s to mean sample standard deviation. And so that it's clear to you when I've written a capital S, I'm going to put these little hooks. It would be very unlikely that you could confuse a sample space with a sample standard deviation because the contexts are completely different. But just to make sure, I'm going to write my S in kind of this funky way. Let's look at a couple of examples of sample spaces, and as we talk about those, I'll also get into what a simple event is as opposed to an event. I mentioned that we were talking about probability experiments. An event is an outcome or a collection of outcomes in a probability experiment. An experiment doesn't mean you're going to have bubbling chemicals or steaming pipettes or anything like that. If you do something and something happens at random, that's a probability experiment. And two very common examples of probability experiments are flipping coins and rolling dice. So to come up with our sample spaces and to discuss what I mean by a simple event, we're going to talk about the sample spaces involved with flipping one coin and rolling a die. Example 1. A coin is flipped. I want to come up with the sample space of all possible outcomes of that experiment. Well, when we flip a coin, what we're usually interested in is the face that lands up when it's done flipping. There are two possible outcomes. It could land heads up, or it could land tails up. Those are the only two possible outcomes of this experiment, and I've listed them inside of these curly braces, indicating that this is a set. That is the set, the collection of everything that can happen when you flip a coin. This is an example of a sample space. I've listed everything that could possibly happen, and these are simple events. I can't break them down any further. Example 2 says a 6-sided die is tossed. When we talk about dice in this class, we're always talking about normal cubic 6-sided dice, not those golf ball sized 100-sided Dungeons and Dragons dice, right? Just a cubic die. And when you roll a die, what we're usually interested in is the number of pips on the top face, right? So if it stops rolling and the top face has 5 pips on it, we call that a 5. So on a 6-sided die, there are 6 possibilities. You could roll a 1, or a 2, or a 3, or a 4, or a 5, or a 6. Those are the 6 outcomes of this experiment. Those are the simple events. I could have also described the outcomes as either being even numbers or odd numbers, because one of those two things has to happen. When you roll a 6-sided die, you either roll an even number or an odd number, but those aren't simple events. If I were to write it like this, with my set being even and odd, while that is a list of everything that can happen, those are not simple events, because even can be broken down into the more basic outcomes 2, 4, and 6, and odd can be broken down into the more basic outcomes 1, 3, and 5. So while even and odd covers all of the possibilities in this experiment, we wouldn't want to use that set for probability purposes because it's not a list of simple events. Those can be broken down further. We want to use the sample space we came up containing the simple events. We don't want to use this one where we have events that can be broken down further. Okay, so now we have a notion of what a sample space is and what a simple event is. Let's talk about the formal definition of probability. This is sometimes referred to as the classical approach to probability. The probability of an event A in an experiment with a sample space S is the number of outcomes favorable to A divided by the number of simple events in S, provided that S consists of equally likely outcomes. This might sound complicated, but this is actually pretty intuitive. Basically, this says you take the number of ways your event can happen in the experiment, and you divide by the total number of things that could happen in the experiment, as long as that list consists of equally likely outcomes. That's how you find probability. This is something you already know. The one part that some people don't consider when assigning probability is that all of the outcomes they're considering have to have the same chance of occurring. But the basic notion is pretty straightforward. We're just going to make a quotient out of the number of ways that our event can happen and the total number of things that can happen in the experiment. The notation that we use for probability kind of looks like function notation from algebra. The probability that an event A occurs is denoted by P for probability, then a set of parentheses, and inside of the parentheses, we write the event or the name of the event. So here we have P and then A in parentheses because the event is A. And the way you would read this is you would say P of A, just like you say F of X in algebra. Oftentimes we'll know exactly what event we're talking about though, and rather than writing a letter in there, we can write a description of the event. And I'll show you what I mean in our first example. I also hope that first example will convince you that you're already familiar with this concept of probability, that this definition is just really made sound more complicated than it is. Here's our example. A fair coin is flipped. A fair coin is a coin that's machined so that both sides are equally likely to come up. Find the probability that the coin comes up heads. So I've got the sample space for flipping a coin. We've got H for heads and T for tails. And what we want to do is find the probability that the coin comes up heads. I'm using my probability notation here by describing the event inside the parentheses. I don't want to write P of A because we haven't defined what event A is. So instead I'm writing the probability notation by describing the event inside the parentheses. Okay, let's go back to our definition. The probability of an event is found by taking the number of outcomes favorable to A and dividing by the number of simple events in S, provided that S consists of equally likely outcomes. Well, we've said that the coin is fair, and if the coin is fair, that means that these two outcomes are equally likely. So the denominator is the total number of outcomes in the sample space, which is 2. There are 2 outcomes, heads and tails. The numerator is the number of outcomes favorable to A, which means the number of ways that A can occur in the sample space. If I want to find the probability that the coin comes up heads, well, I count how many ways the coin comes up heads in the sample space. And there's only one outcome associated with that. So the probability that the coin comes up heads is 1/2, 1 divided by 2. Of course, we could convert that to its decimal equivalent, which is 0.5, or we could convert that to its percent equivalent, which is 50%. And it's the last of these that I'm betting you would have guessed if I hadn't gone through all of this formality. If I had just asked you, what's the probability of getting heads when you flip a coin, you probably would have guessed 50%. And why do I think you would have guessed that? Well, you've got good number intuition. Half of the outcomes are heads, and so the probability would be 50%. That's basically what this definition says. It says it in the nerdiest possible way, and it shores up some misconceptions that people have about probability. But basically, this just says take the number of ways your thing can happen and divide by the total number of things that can happen, and that's the probability of your event. Let's look at some more examples with the die, because the coin doesn't give us too many options here. But when you're rolling dice, you've got a lot more simple events to work with. Example 2, a fair 6-sided die is rolled. So when I say the die is fair, it means it wasn't weighted in some way so that you could cheat and get one side to come up more often than the others. All of them are equally likely. Find the following probabilities. So part A says, find the probability that a 5 is rolled. Back to the definition. The denominator of the probability is the number of simple events in the sample space. I've listed that sample space at the bottom here. There are 6 possible outcomes. 1 pip, 2 pips, 3 pips, 4 pips, 5 pips, or 6 pips. And so the denominator is 6. The numerator of your probability is the number of outcomes favorable to your event, which means the number of ways in the sample space that you could roll a 5. Well, there's only one way to roll a 5, and that's if you wind up with 5 pips on the top face. And so there's one favorable outcome, and we say that probability is 1/6. Now, 1/6 turns out to be a non-terminating decimal. It repeats, but it goes on forever and ever and ever. Because of that, writing the probability as 1/6 is probably the best way to do it. But we could also approximate this by rounding that decimal somewhere. Like it comes out to about 0.167. And we can turn that decimal into a percent. That's 16.7%. Neither of those last two representations are exact probabilities, but they're close. As we delve further into this topic, we're going to be pretty reliant on the calculator, and we're going to wind up getting decimal results from the calculator, so we'll be rounding a lot using the calculator anyway. But it's probably best to express this answer as the fraction 1/6. Part B, find the probability that an odd number is rolled. Well, this isn't a simple event because there's more than one way to roll an odd number. Thinking about our definition again, the denominator is the number of simple events in S, which is still 6. There's still 6 outcomes in the sample space. The numerator is the number of favorable outcomes to A. In other words, the number of ways that you could roll an odd number in this experiment. Well, 1 is an odd number, and 3 is an odd number, and 5 is an odd number, and that's 3 outcomes in the sample space that are favorable to our event. So this probability is 3/6. And some of you might be twitching a little bit here because you're just dying to reduce that fraction. And I'm going to reduce it too, but I'm going to tell you right now, I don't care if you reduce your fractions. 3/6 is a perfectly acceptable final answer in my class. But it probably is better to write it as 1/2, even though at your level, I'm sure you can see 3/6 and 1/2 are the same, and so it doesn't really matter. You could also convert that to a decimal, which we said was 0.5, or you can convert it to a percent, which is 50%. I don't need all of those representations. I would take any of them, including the fraction that isn't reduced. Any of those 4 answers is acceptable. Here I have no issues with any of these because they're literally all the same number. In the first example, 1/6 and 0.167 aren't actually the same number. They're just close. So if I asked for the exact answer, you'd have to give me 1/6. Part C says find the probability of a number greater than 2 being rolled. The denominator is 6 because there are 6 outcomes in the sample space. How many numbers in the sample space are favorable to our event, greater than 2? Well, 3 is greater than 2, and 4 is greater than 2, 5 is greater than 2, 6 is greater than 2. That's 4 outcomes in the sample space. You could leave your answer as 4/6. It does reduce to 2/3. You could convert that to a decimal, although you'd have to round it because that's a non-terminating decimal. You could convert that decimal to a percent. That would not be an exact answer. Any of those would be acceptable. Having these 3 examples on the screen gives me an opportunity to talk about what these probabilities are telling us. The probability of an event is the likelihood that the event will occur. It's the ratio of the time you can expect that event to occur in the long run. The first answer here says that the probability that a 5 is rolled is 1/6. What does that answer really mean? It means that if you were to roll a die many times, over the long run, the fraction of the time, the proportion of the time that you would get a 5 is about 1 out of every 6 rolls. Our second example says the probability of rolling an odd number is 3/6. So over the long term, you would roll an odd number 3 out of every 6 times. And this is one of the reasons why I don't really care if you reduce. It actually makes it easier to compare these two by not reducing. You can see that it's more likely to roll an odd number than to just roll a 5, and that should be obvious because 5 is one of the 3 odd numbers, so you're giving yourself more opportunity in the second case than in the first case. But even if you didn't recognize that, you can see it based on the numbers. 3/6 is a bigger fraction than 1/6, and therefore the likelihood of rolling an odd number is bigger than the likelihood of just rolling a 5. Again, your intuition would tell you that because 5 is one of the 3 odd numbers you could roll. But even if you don't have that containment idea going on, you can still use probabilities to make a comparison. What's more likely, rolling an odd number or rolling a number greater than 2? Not all numbers greater than 2 are odd, so we don't have that containment idea here to guide us. But we can just look at the probabilities. 4/6 compared to 3/6, well, 4/6 is the bigger probability. So that means that that event is more likely to occur. It's more likely that you'll roll a number greater than 2 than it would be to roll an odd number. So in essence, we're saying the bigger a probability is, the more likely it is that event will happen. And the smaller probability is, the less likely it is to occur. That's how we interpret probabilities. Let's talk about a couple of special cases here. We've got the same scenario. A fair 6-sided die is rolled. I've got the sample space below. We're going to find 2 more probabilities, and they're going to look silly, but it's going to allow us to talk about those borderline cases in our definition of probability. D, find the probability that a number less than 7 is rolled. Well, let's see, the denominator would be 6, because there are 6 outcomes, and the numerator is the number of outcomes favorable to the event rolling a number less than 7. Well, all of these numbers are less than 7, all 6 of them. We get 6 out of 6. And I would accept that answer, but you can divide 6 by 6 and get 1. Or you could turn that into 100%. Remember that we said that 1 was the largest possible probability that you can assign to an event. And it happens to be assigned to an event that must occur. It happens 100% of the time. All of the numbers in this set are less than 7. This is guaranteed to happen, and it has the maximum probability. We call an event like this a certain event. A certain event is an event that must occur. Let's look at part E, the other special case. It says find the probability that an 8 is rolled. Well, the denominator is 6 because there's 6 outcomes in the sample space. And how many of those outcomes are 8? Well, none of them are 8s. It's impossible to roll an 8 on this die. There are 0 outcomes in the sample space that represent rolling an 8. So we get the fraction 0 out of 6. And you can leave your answer like that, but of course 0 divided by 6 is 0, which is 0%. And we said that 0, or 0%, is the smallest possible probability that you can assign to an event. And it's assigned to events that cannot happen. We call these kind of events impossible. It's impossible to roll an 8. And because it's impossible, it has probability 0. So these represent examples where you get those most extreme possible values of a probability. If the event has to happen, if it's guaranteed to occur, it has probability 1. And if it cannot happen, if it's impossible, it has probability 0. I want to remind you, by definition, all probabilities are between 0 and 1 inclusive. Probabilities can never, ever, 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 ever be negative, because remember, the numerator of the probability is the number of outcomes favorable to the event. You can't have a negative number of possible outcomes. That doesn't make sense. And probabilities are never, ever, 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 ever bigger than 1. I know I went a little bit weird on you there, and that wasn't even editing. That was me just freaking out. But you cannot have probabilities bigger than 1. Go back to our definition. The numerator has to be a number of outcomes from the original sample space. That can't be bigger than the number of events in the sample space. You can't ever get an answer bigger than 1 by definition. But students will still give me answers bigger than 1, and it hurts my feelings. The reason why students will give me an answer bigger than 1 is not because they don't understand this rule, it's because they're not thinking when they get an output from the calculator. Let me give you an example. If you roll 5 dice, the probability that all 5 of those dice come up with the same number is 1 in 1,296. Any of you that have played Yahtzee before where you roll 5 dice, the probability of rolling a Yahtzee on your very first turn is 1 in 1,296. Now, if you ask the calculator for the decimal version of that, it's going to give you an answer that looks like it's bigger than 1. But that fraction is clearly not bigger than 1. It's a very small fraction. It's a very small probability. I hope you notice that there's an E in this number. Right? That should stand out to you. Hopefully the E will tell you that something weird is going on. That's the calculator's way of giving you scientific notation. It's saying, please, before your instructor has an aneurysm, move that decimal point 4 places to the left. This is actually 0.0007716, blah, blah, blah. It's a very, very small probability for an event that's not very likely to occur. If you're not thinking when you calculate a probability, you might tell me that the probability is 7.716, but probabilities are never, ever, 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 ever bigger than 1. Look for that scientific notation. I tend to grade very harshly when students give me answers bigger than 1 because probabilities are never, ever, I'm not doing that again. Watch out for that. Either you've misread your calculator output or you've made a mistake in your calculation. Okay, with that little bit of psychosis out of the way, let me get to a non-example. I want to talk about an example where people misuse probability because there's a part of that definition that really, really matters that people often overlook. So this is a non-example. I want you to conduct this experiment. I want you to clap your hands. I'll wait. All right, some of you were cool and did it, and some of you were lame-os. There are 2 possibilities. Either, when you did that, you turned into a duck, or you didn't turn into a duck. One of those 2 outcomes has to happen, right? Either you did or didn't turn into a duck. One of those 2 things has to occur. If you're not carefully following our rules for finding probability using the classical approach, you might make this mistake and say, well, the probability that you turned into a duck is, well, let's see, there are 2 outcomes in the sample space, and one of them says you turn into a duck. So the probability that you turn into a duck is 1/2? That's ridiculous. That doesn't make any sense. There's no way that in the long run, 50% of people who clap their hands turn into a duck. What's the part of the rule that we're messing up? The sample space must consist of equally likely outcomes. That's an important part of this definition. If we go back to our example, our non-example, we've got 2 events listed in the sample space, but they don't have the same probability of occurring. One of them is going to happen way, 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 way more often than the other, because I'm pretty sure nobody's ever turned into a duck by clapping their hands. This is a misuse of probability, and I admit this one is kind of silly, but people use this logic all the time. They'll say, well, it's 50-50 because either this is going to happen or it's not. But that's not how probability works. You can't just say because there are two outcomes, there's a 50-50 chance. So don't be one of those people who misuses probability in that way, because this is nonsense. Okay, one more definition with a couple of examples to go with it. The idea of a complement. The complement of an event A is the collection of all outcomes in the sample space which are not favorable to A. If you were learning this on Mickey Mouse Clubhouse, we'd be calling this the opposite. But because we're in Big Boy and Girl Land, we're going to call this the complement. But basically, the complement is the opposite within that experiment. It's like the collection of all ways that your event does not happen. Your author likes to use a prime notation for the complement. The complement of A is denoted by A with a little prime next to it. We're just going to read this as A complement. And there's an important math rule that goes along with this one as well. The probability of the complement of an event is 1 minus the probability of the original event. This is something that you already know, but when you write it in symbols, it makes it seem more complicated than it actually is. But it's a simple idea. It says if you want to find the probability of the opposite of an event, just do 1 minus the probability of the event. Some people find this rule is easier to understand when you write it with percents. The probability of the complement of an event is 100% minus the probability of your event written as a percentage. As long as P of A is written as a percentage, you can apply this rule. You can also rearrange this rule in a couple of different ways, but I just want to demonstrate the rule for you a couple of times. But before we get into any of that, I just want to show you that you already know this rule. I'm just going to say an example. Suppose you go into a room and you notice that 1/3 of the people in the room are wearing red shirts. What fraction of the people are not wearing red shirts? Well, it would be 1 minus 1/3, which is 2/3. You might not even have to do it as 1 minus 1/3. Your brain might just tell you that it's 2/3, but that's a subtraction step that gets you there. You know this rule. We write it in this nerdy way so that we can apply it in mathematical situations, but this is an idea that you know. You know the percentage version as well. Suppose they did a study and they said that 20% of all people like peanut butter and marshmallow fluff sandwiches. And we wanted to know the percentage of people who do not like peanut butter and marshmallow fluff sandwiches. Well, that'd be 100% minus 20%, which is 80%. And those 80% of people are wrong because fluffernutters are delicious. But that's beside the point. You guys already know this rule. If you want to find the probability that something doesn't happen, you just subtract from 1 or subtract from 100%. Let's do a couple of examples in written form just to make sure you understand. Here's a gambling example. The probability of winning when betting on red on a roulette wheel is 9/19, 9 over 19. What is the probability that you lose when betting on red? Well, winning and losing are complements, opposites. So the probability that you lose when betting on red is 1 minus the probability that you win. And the probability that you win is given, it's 9/19. So we can just do the arithmetic. You get a common denominator, and you subtract the numerators. If the probability that you win is 9/19, then the probability that you lose is 10/19. And some of you might say, well, I don't need to do that fraction arithmetic, I can just see that. That's okay, you don't have to show me that work. But of course I want to show the work, not only because that's just what instructors do, but also in case you're a little bit shaky on your fraction arithmetic, I wanted to remind you that you have to get a common denominator when you subtract. By doing this arithmetic, you can see that it's more likely that you lose than win, because there's a bigger probability associated with losing than winning. Let's do a percent example. The probability that a randomly selected American has diabetes is 9.4%. What is the probability that a randomly selected American does not have diabetes? Well, the probability of not having diabetes can be found by using this complement idea. Now, because this was written as a percent, I might choose to do this as a percent. I could do 100% minus 9.4%. And 100 minus 9.4 is 90.6. That's a 90.6% chance of not having diabetes. I could also do this by using the decimal. I could start with 1 and subtract the decimal version of 9.4%. I move the decimal point 2 places to the left, and then I subtract them in decimal form. That would be 0.906, which of course could be converted to 90.6%. So there are two examples of the complement rule that we'll be using in more complicated situations later. So I hope this gives you an idea of what probability is and how it's calculated. We'll be talking about this more throughout the unit. If you have any questions, let me know.